Where did Earth and the other planets, especially the rocky planets, come from? So the long version of that is going to follow, but the quick version is that Earth formed from an agglomeration of meteorites, and the meteorites themselves were built up from pre-planetary dust and rocks. And that's a short story, but the longer version of that we can get into a little bit. So let's talk about that. So how did the Earth itself form? So we talked previously about the earth sciences and the study of the Earth being set in a group of other sciences. And so the earth sciences are one of the planetary sciences. When you study the other planets, that's what makes up the planetary sciences and how they formed. And then the planetary sciences themselves are part of astronomy, and that all is part of cosmology. So in order to really talk about how the Earth formed, we have to talk about a few other things, like how the solar system formed, right? And in order to talk about how the solar system formed, we have to talk about the Big Bang and how the universe itself formed, because our solar system is just one object within the universe. So we'll do a little bit of kind of a background cosmology here, right? So the Big Bang is the major and main theory about the origin of the universe. There used to be other ideas that the universe had always existed and perpetually existed and just kind of looped around itself. But that kind of all started to give way to the Big Bang theory. And the Big Bang is kind of a derisive term. So when it was first being proposed, people rejected it because it sounded kind of strange, that you had this kind of explosion of space and matter. And so they kind of made fun of the idea by calling it the Big Bang theory. The more formal name for it is inflation theory, right? That space rapidly expanded and inflated like a balloon. But this idea, even though it wasn't very popular at first, has stood up to a lot of different tests and attempts at falsification. So people have tried to disprove inflation theory, the Big Bang theory, many times over, and it's stood up well enough for us to continue to use it, keep using it. So according to the Big Bang theory, the whole universe starts around anywhere from 10 billion to 20 billion years ago. So that's just the widest window that you can have for this theory, right? We can narrow it down quite a bit more with some other techniques, right? But for the theory itself, it's a rather large window. And so before the Big Bang, all the matter and energy and material and space in the universe was compressed into a single point. So not just a small ball, right, but an actual like mathematical point that has no dimensions, right? So like a line has two dimensions, right? A square has a line has one dimension, a square has two dimensions, and a cube has three dimensions. If you have 0 dimensions, that's a point, right? So that's how everything was in before the Big Bang. And as the Big Bang occurs, and no one has any idea what causes this inflationary period, what causes the Big Bang or what triggered it. That's something people are still trying to understand. But once it starts, everything starts expanding in all directions, like an explosion. And so now, because all of the matter and energy, especially, was really concentrated into a small volume in the early instance of the Big Bang, the temperature of everything was very high. So things like solid material was just melted, right? If you take a rock and you heat it up in a furnace, it'll melt into molten rock. If you heat it up even more, it'll turn into plasma. And if you start heating up things even more, the bonds that hold atoms together start coming apart, and you start melting even atoms themselves in a way. So you had nothing like what we have today in the first few instants of the Big Bang. So the temperature was extraordinarily high, and then a few seconds into the Big Bang, the temperature had cooled to around, some estimates are around 5 billion degrees Celsius, right? 5 billion degrees. And that's cool enough for some things to start happening, right? So things like protons and neutrons were able to be formed, right? Before that, you melted the protons and neutrons. They couldn't exist. So they were just broken down into their individual quarks and things like that beforehand. So now the universe is starting to form things that are at least theoretically recognizable to us as matter, like protons and neutrons. And as it continues to expand, it continues to cool. And as it cools, you're able to then form new types, or not new types, but new, not new, but just different stages of matter. So around 300 or 400,000 years after those initial seconds of the Big Bang, things have cooled enough that you have a heated nebula of hydrogen and helium gas, mostly hydrogen gas. So hydrogen is a atom that only has one proton, right? And so it's the simplest way to have things, right? Once you formed a proton, you've basically formed a hydrogen atom, right? And so for a long time, this is all there is in the universe, right? It's too hot to form anything else. So the distribution of that hydrogen gas was not perfectly even. And if we think about the way that physicists tend to or like to describe things, like to simplify things, we make everything very evenly distributed. There's no randomness in a system. There's not a lot of things here or a lot of things there, right? They remove friction and they don't account for all kinds of things in physical ideas in order to simplify them. But reality is always more complicated than that, right? So the initial universe, it was not totally evenly distributed. There was some clumpiness to it. And it's that clumpiness that results in or allows for the structures, grand structures that we see today that make up the universe, the arrangement of different galaxies into supergroups and things like that. So in these clouds of hydrogen gas, you start to, because there's this clumpiness, non-random distribution, the particles of gas start to stick to each other and they start to collide with each other. And then they get big enough where they can actually have a gravitational effect on the materials around them. And so they pull more and more material into them. And eventually you start forming things like stars. So stars are some of the first things to form that we would even recognize in the universe. And they usually start as a nebula, as this cloud of dust and gas. And so now today, around 15 billion years after the start of the Big Bang, we've gone through many generations of stars, right? There have been entire sets of stars that have formed and died out, and then other generations that have been born from those materials. So what's some of the evidence for the Big Bang, right? So it was first proposed by Edwin Hubble, who has the Hubble Space Telescope named after him, right? Fairly well-known object, the Hubble Space Telescope, named after Edwin Hubble. So it's only in the 1930s that this idea even comes up and is proposed. And he calls it, sometimes called inflation, he calls it the expanding universe theory. And the idea is that the whole universe is expanding and has always been expanding. And if you run that expansion backwards, right, then you would arrive at a single point. So he could see that everything was moving away from each other. He could look at all the different stars and galaxies and things like that. And he could examine them and see that they were moving away from each other, right? And if you tracked back that movement, logically you get to a very small space and then eventually a point, right? And so that's kind of the inspiration for his idea. And then he actually had to not prove it, but get evidence for it. So Hubble was dependent on something called redshift. So redshift is kind of a Doppler effect on the light emitted by stellar objects in the universe that allows us to determine what direction they're moving, if they're moving away from us or towards us, right? So the light spectrum emitted by them could be shifted to the red part of the spectrum or to the blue. If it's moving away, it looks redder. If it's moving closer, it looks bluer. And when they started looking at objects and measuring this Doppler shift, they saw that everything was redshifted. That there weren't some things that were flying away from us and other things that were coming towards us, right? Everything was redshifted. And they kind of realized that, well, we're not at the center of the universe and everything's not moving away from us. So what's going on? And they started to realize that everything is moving away from everything else. The distance between all objects in the universe is getting greater, right? And so that is the expansion that Hubble talks about. Right, so we can see some of the first light from the first galaxy still 15 billion years after it formed, right? So why is that? Well, because those objects are 15 billion light years away from us. And so we can still observe these very old objects, even though they're no longer around. It's just that their light has taken a long time to reach us. So 1 light year is the distance that light travels in a year, and it's around almost 10 trillion kilometers a year that it can travel. Oops. Okay. So I mentioned nebula before. So these are some photos of nebula. So you can see that they're made up of gas, and that gas is only visible because there are stars. You can see here 2 stars and many stars in these other ones. There's stars that are forming in them, putting off light and illuminating the gas and dust around them inside the rest of the nebula. Otherwise, it would be black as space, right? And so these are a set of nebula, or a nebula that is sometimes called the pillars of creation. It's a huge pillar-looking cloud of hydrogen and helium gas and some other dust. And we have many stars that are forming within it and illuminating it. This picture is from the Hubble Space Telescope, named after Edwin Hubble. So how do stars form? They form as the nebula that they're within starts to, or that they will be in, starts to collapse under the force of gravity. And as that material gets closer and closer and denser, its temperature starts to go up. So you can kind of imagine something being compressed, and the temperature inside of it gets warmer as everything's being compressed. And the gravity can become so high as once enough material accumulates, that the individual atoms now start getting pushed together and get fused together, right? And so that's nuclear fusion. And doing that releases a tremendous amount of energy, the energy mostly present as light, right? Or actually, I don't know if it's mostly light or other types of radiation, right? But it produces a lot of light. So once you start having nuclear fusion, we like to say that the stars are burning their fuel and they're producing light and giving light off. So that's a nuclear kind of reaction. When you do that with 2 hydrogen atoms, they produce a helium atom, right? Because they're fused together now. The nucleus of the atom now has two protons instead of 1, and so it's now helium. So nuclear fusion is sometimes also called nucleosynthesis, and it's called nucleosynthesis because it produces some new material. You've synthesized some new material. So fusion is, again, the joining of these smaller atoms to produce larger ones. And so that can happen with hydrogen fusing to helium. Then you can take the helium, fuse another atom to it, and you get lithium. And you can work your way up the periodic table to produce new elements. So the simplest type of reaction is the burning of hydrogen to produce helium. Fusion releases a large amount of energy in the form of heat and light. And stars then are natural thermonuclear reactors, which is kind of a weird way to think of them, probably, right? Okay. So here's the periodic table that I just mentioned. And in another talk, I talk about what all these different symbols mean. But so we had our helium here, our hydrogen here, and it has 1 proton, and then there's 1 electron moving around it. So when you fuse 2 of them together, you get the helium atom. And then when you fuse a helium and a hydrogen atom together, you get lithium. And perhaps if you fuse 2 helium atoms together, you get beryllium. And you can move up this table, generally up to about when you get iron. And then once you get iron, you can't fuse anymore to get higher and higher elements. You have to have something called a supernova in order to make them. So stars naturally produce the elements that we're familiar with. And without stars, they wouldn't be around, right? There might be some hydrogen and helium, probably like a little bit of lithium in the universe, right? But not all this other stuff that we see. So these elements that make up everything that we're familiar with, right? That do all the chemistry that produces the rocks and the minerals and the animals and things around us, it wouldn't even exist. So without stars, none of us exist. And without stars, the Earth doesn't exist, right? Okay. So the first stars, like I said, that first generation of stars were producing, burning up hydrogen and helium. And then as they got heavier and heavier and you got bigger stars, they could force together elements to produce things like iron. Once you have a supernova, which is an explosion of a very heavy, massive star, you can produce elements heavier than iron. And so stars, in a way, have a life cycle, right? They have a birth, right, as they form from a nebula, and they have a death as they explode into a supernova, or some other types of star deaths can occur. So the sun right? The sun that is around that our planet orbits is, we think, a third or fourth generation of star. It was not one of the first stars to form in the universe, and it wasn't even one of the second ones. It formed when there was already a lot of other elements present. So there have been two or even three generations of stars prior to our solar system forming. It seeded the universe with all of the elements that we're familiar with today, right? Up to iron and then beyond in the supernova. You can kind of imagine that first generation of stars, all you've got is hydrogen, maybe sometimes and helium, and then maybe sometimes you can get up to iron, right? But it's not until you start having supernova, and you have to have a lot of them, right, in order to spread this material throughout the universe, that it's common enough to form, be found on planets and things like that. It was only up to iron, right, for that first generation, and then you had to have these supernovas occurring in order to spread all the heavier elements out that we are familiar with. So our solar system really requires, or at least the life that we know and the world that we know requires multiple generations of stars to spread this material everywhere. So our solar system starts off just like every other star, right, as a nebula. And so sometimes it's called the pre-solar nebula or just the solar nebula. And so the solar nebula that our sun and planets and us formed out of is 99.9999% hydrogen and helium, right? Stuff from the Big Bang. And a tiny percent, not 1%, not 1/10%, not 1/100%, but 1,000th of 1%, are all the other elements. All the other elements are only 1,000th% of the solar nebula, because we're only in a third or fourth generation of stars. I mean, maybe in theory, if you had 30 or 40 generations of stars, you start increasing the amount of all these other materials, and you can maybe make a significant impact on how much the ratio of stuff of helium to non-helium there is, right? So even with just this tiny little, unmeasurable percent, right, 1 part per thou, we would not even, if you dropped 1 part per thou black paint into white paint, you wouldn't even see the difference in the color of the paint. So a tiny little amount, but that's everything that we're familiar with. So we are, you've probably heard this before, it's in lots of songs, but it literally is true that we're made of the dust and remains of stars, right? The atoms that were in those stars are in our bodies, and that's what makes us up. So to form a solar system now, you have to, not just the sun, right, not just the star, but to form the whole solar system, we have another theory that we call nebular condensation theory. And so these are all ideas that they're sometimes challenged and changed, and they're being tested even today, right? And they're not just settled and left as they are. So in nebular condensation theory, the idea is that you have clouds of gas and dust that is collapsing to form a star, and at the center of that collapsing cloud, we call the star a protostar, and as it collapses, it starts to get some spin to it. As the radius starts to decrease, it starts to turn and produce some spin. And so as it's collapsing and spinning, you change from just a cloud-like nebula, a spherical nebula, to something called a protoplanetary disk. And you can kind of imagine a large clump in the center of this protoplanetary disk, and then a lot of material spinning around it, like a record player or a CD or anything that you have to think of that's familiar to you as that kind of thing. And so it's within these protoplanetary disks that planets can start to form. So what's in that protoplanetary disk, right? We started with a nebula that's almost exclusively hydrogen and helium and a little bit of all the other elements. And as it collapses, most of the hydrogen and helium is going into the star. It's dragging all the other stuff in with it. All the iron and other things are descending into the star, the protostar rather. And once they're in there, they're not going to get out, right? They're not going to really be leaving there. So all this material starts going into what's going to become the sun, and then a little bit of it is left, and it starts rotating like a disk around the protostar. So that disk around the protostar is still mostly hydrogen and helium, and a little bit of all the other elements, right? And it's all very hot because the sun is very active. Stars are very active when they're first formed, and they put out a tremendous amount of heat. So you don't have ice crystals or solid materials very close to the protostar. Farther out from it, things are a little bit more, there's more options for things, right? They can be far enough away that you can have things like ice and frost and solid material condensing out of the protoplanetary disk. And if you can kind of think about this, these materials are from other generations of stars, right? It probably themselves had solid materials during their lifespan around them, right? So some of the materials and grains, little chips and grains of solid material that are around the early protoplanetary disk are pre-solar materials. There's stuff from before our sun even existed. Things that are close to it, any of these pre-solar grains that are close to it are going to get melted and kind of vaporized, and they're gone, right? The elements are still there, the atoms are still there, but the object itself, the little grain of rock and dust, is gone. But far out in the solar system, those materials are still present, potentially. And so sometimes we find them in things like comets, which normally exist very far out in our solar system. Right, so here's now a picture of that nebula that's collapsed into a disk, or rather an illustration. This is a picture, an actual photo from the Hubble Space Telescope of protoplanetary disks within the Orion Nebula. So you can kind of see here's an object, and perhaps it's a protostar, and it's drawn in maybe everything around it, so there's kind of a gap between it and the rest of the nebula. And here are ones where you can really convince yourself that you see a star-like object and a disk of dust rotating around it, one side being illuminated by the light of other stars and things like that. So all of these things are stars within these nebulas. So sometimes the nebula produces more than one star. So this object is in the Orion Nebula, which is around 15,000 light years distant from us. So very, very far away. And so this scene that we're seeing is also 15,000 years old. It's 15,000 years ago. Things have changed quite a bit in that area, presumably, since it was taken. That image was taken, or since that image was first produced and reached our telescopes. So now in the inner part, like I said, in the inner part of the nebula, things get vaporized, and new dust can start to condense as it cools off, as the star becomes less active. So you've had some pre-solar material, you vaporize it, but then eventually things can get stable enough that it can cool back down, and you start forming new bits of dust and solid rock and minerals. So the new dust will start to now accrete and stick together. It grows by something called accretion, by materials just sticking together. Perhaps it's just electrostatic forces that are causing them to stick at first, but then they just like the star in the early nebula, get big enough that they can produce gravity and draw things to them. And everything is also spinning around in this protoplanetary disk, and as they do that, they're not just standing still, they're actually moving around relative to one another, and they can crash into each other and clear out areas around them. So this slowly, piece by piece, these bits of dust and grains and minerals start to accrete to form things that today we would call like a minor planet. Like Pluto, well, Pluto's a dwarf planet, but it's a very small planet. And there are probably a lot of Pluto type of objects out there in the early solar system. And there's still many Pluto-like objects, dwarf planets, that still exist in our solar system today. Yeah. So this is just showing that picture. Yeah, I guess I should have been clicking through this. But so we have our early sun, these clouds of material, and the protoplanetary disks. And here we have these. This is a nice illustration, isn't it? We have these shadows coming from the minor planets as they're starting to form, and then we eventually get to something like this, where most of the material has been sucked into the star, and a tiny bit has been left in the disk, and now most of that material within the disk has been accreted into a bunch of clumps, which we call planets, right? And you can kind of imagine the earliest times of the solar system, you might come across a solar system in this stage of formation, and you see something that basically looks like a planet, and it crashes into another planet over time, and they're all crashing into each other and disturbing their orbits. And you can imagine when two large planets crash, or two large minor planets crash into each other, the gravity effect of that alone starts putting all the other minor planets off kilter, and they start crashing into each other also. There's a long period of time before, when you have something that we would all call a planet, but the orbits are just not stable because things are crashing into each other. There's a long period of time before you have stable orbits and planets together like we have today. So here's a graphic of our solar system. We have Mercury, Venus, Earth, Mars, right? These are the terrestrial planets. They formed mostly out of the hard rocky parts of that protoplanetary disk, the grains and minerals and accreted objects, right? Farther out into the solar system, we have the gas giants like Jupiter, Saturn, Uranus, Neptune, and then things like Pluto, Eris, other dwarf planets. And so as you move away from the sun, the temperature in the solar system, or the early solar system, or the protoplanetary disk, decreases. And so in places like where the rocky planets have formed, you have vaporized and blown off all of the light gases, right? So mostly the gases are being drawn into the sun, right? But the heat of the sun also melts and pushes away the gases and ice that are present here, leaving just the heavier, more stable rocky parts like the dust and grains of rock. So that's why these planets here, any planet that forms in that rocky zone, are going to be terrestrial planets, right? They're going to be made up of rock and solid material. So even though Mercury and Mars are far apart and very different, they still have a similar origin, right? They're all formed from the rocky parts left over once you blow away the clouds of hydrogen, helium, and ice gas from the solar system. So all of these terrestrial planets are made from the same thing. If you grab the chunk of Earth and then you grab the chunk of Mars and you compare them, they're going to look similar. To a geologist, they're going to look identical, right? They're going to have the same minerals. They're going to have the same rock types, or at least the same basic rock types. And if you do the same for Mercury and Venus, you're going to see that also. So they're all the same material, basically. Now, the other major division with our solar system then are these gassy giant planets, and so they're made up of, like I said, the gas that was left. So as the sun was blowing away the ice and gas from the inner zone of planets, that left mostly, mostly the gas out in the outer zones. So now they're far enough away from the sun that they're not getting pushed away into the void, and they make up the majority of what's there. Remember, 99.999% of what's in that solar nebula and what's in that protoplanetary disk is helium and hydrogen, right? So these planets have a tremendous volume because there's a huge amount of that material there, and much more material than there is in the terrestrial planets. And those planets are very large. They're not solid or terrestrial. There certainly would have been solid grains and minerals present in those zones. And the further out you go, perhaps the fewer solar grains you have and the more pre-solar grains you have. But they're just wiped out. And they're so rare compared to the amount of hydrogen and helium gas that's present. So we have these gas giant planets that are dusty gas, right? And as we move even further out, we have things like comets beyond the planets, right? That are made up of frozen ice and frozen gas. So our main, focus here is this first zone, the rocky and terrestrial planets, because we want to know, how did Earth form, right? So we've talked a lot about how the solar system forms and how the planets in general have formed, but our main concern is how Earth formed. And Earth's formation is the same story as the formation of Mars and Venus and Mercury. It's just at a different distance from the star that is the sun. So we have this generalized idea, this theory that we call nebular condensation theory, which started off as a hypothesis, went through lots of testing, hasn't, and has stood the test of time. It is still a good theory, a good hypothesis, so we tend to refer to it as a theory. And so what is that nebular condensation theory? Again, in brief, right, it's that within a solar nebula, dust starts to condense, it gets very hot, forms a star, and the dust starts to accrete to form small particles that grow over time by crashing into each other and accreting into larger and larger planets. So that's the shortest version of that condensation theory, right? But things aren't as simple as that sounds, right? I mean, that's like how a astronomer or physicist might describe the formation of a planet, and they would stop there. Basically, they'd say, "Well, you've got the dust; it accretes enough to the point that you have a Earth-sized object, right?" But there's more that's going on there, right? So, how do we know about all of this, right? Well, we know because we have meteorites. And so meteorites are a major piece of information about how the terrestrial planets formed, right? So what are meteorites, right? So meteorites are pieces of other bodies in our solar system that land on Earth, right? So we can have a lunar meteorite. We can have a Martian meteorite. We have those. We can also have meteorites from asteroids and other bodies and objects within the solar system. So when an object lands on Earth or crashes into Earth, we call it a meteoroid. And while it's falling through the atmosphere, we call it a meteor. And then what's left, if anything's left, when it hits the ground, that stony bit or metallic bit or whatever it is called the meteorite, right? So the "ite" ending is what we refer to for rocks. So meteorites are rocks that have come to Earth from space, whether they're from the moon or Mars or the asteroids. In fact, when people first were studying meteorites, they didn't know where they came from. It's not easy to see the asteroids out in space, but it is easy to see the moon, and it's easy to see that the moon is similar to Earth. Like you can see that there is some topography going on there, that there's materials that are present there, and it looks rocky. So people thought that all meteorites were actually from the moon. And they had fallen from the moon to Earth, perhaps being dragged off by Earth's gravity. But we now know that they come from lots of different places. So there's kind of this weirdness where we talk about meteoroids. A meteoroid is that, in theory, whatever the body was that this meteorite that crashed on Earth came from, right? So maybe the moon was the meteoroid, right? Or maybe a particular asteroid was the meteoroid. So it's weird. We have these two names for what's the same thing, right? So people didn't know that asteroids were actually the source of a lot of meteorites for a while. So there's this weird confusion with the names. So the Antarctic is a place where it's easy to find meteorites because there's not a lot of vegetation or anything growing over the ground to hide or obscure the meteorites. They obviously stand out very well against the white icy surface. And it's not that there's, a lot of meteorites that are falling on Antarctica relative to anywhere else. It's just they're easy to find. They're also preserved. They're not buried because there's very low precipitation. Antarctica is kind of a desert. It doesn't have a lot of precipitation. So the object is not getting buried over time by new accumulation of ice and snow. And because it's so cold, chemical reactions are very slow. Chemical reactions that would break down a rock are dependent on temperature, right? So the rate of the reaction is dependent on temperature. And the lower the temperature, the slower the reaction rates. So the less the rocks get broken down. So it's a good place to find meteorites. So they've recovered this meteorite in this picture here, and when they bring it back to the lab, here's a photo of a meteorite in the lab. You can right away see that it has lots of different components, lots of minerals that make it up, and they actually record it with this little cube that indicates the direction that each face was when it was found, kind of like a dice or a die. And so this is the east direction for it. And so these things are kept in storage once they're collected, and they can be sent out to other researchers who want to work on them. And so they might take a sample from it, break it up, and put a very tiny sample or a large sample, depending on what they're doing, into an instrument in order to examine it. So here is a figure that we've looked at in the past. So here we have our solar system. There's the sun, and here is Mercury, Venus, Earth, Mars, and then 2 to 3 astronomical units out is a ring that makes up the asteroid belt. And so the asteroid belt, it's between Mars and Jupiter, and it's made up of a lot of smaller rocky bodies that are called asteroids. And a lot of the meteorites that we encounter are from there. So each one of them has their own, they're colliding with each other. They kind of have their own orbits, but it's not as organized as like the rest of the solar system. So it's not totally chaotic where they're constantly crashing into each other. We can look with good telescopes and see asteroids over a very long period of time. So some of them are extremely old. Some of them are like as long as we've been able to observe them, we've seen them there. So it is relatively stable there. And these asteroids are leftover parts, pieces that failed to accumulate into planets. So a lot of them are older than the planets themselves. But some of them have also crashed into each other and kind of melted themselves and formed new bodies, since the planets have formed. So most of them are pretty small, much smaller than any of the planets. The largest asteroid is about a third the size of Earth's moon, which is about 1,000 kilometers in diameter. But most are just a few kilometers or a few tens of kilometers in size. And then there's also between them a lot of dust. So there's still a lot of dust and loose grains floating around out there. So this is the asteroid Matilda. It has a diameter of around 47 kilometers. This is the asteroid Ida. It has a diameter of 52 kilometers, which I would assume is in this longer axis is the one that they measure. And here's Gaspara with 11, Dactyl with only 1 kilometer. So they have names because they're persistent, and some of them have been around for much longer than others in terms of the scale of the solar system. Over time, the asteroids accrete and grow into the planets that we have now. So let's stop right there for this part, and we'll come back to some of this material and talk about this kind of stuff again. Okay?